Hello students! We continue our discussion of infinite series. In this video, we're going to take a look at geometric series. Let's start with the definition. A geometric series is any series of the form n equals 1 to infinity of a times r raised to the n minus 1. In expanded notation, this is a plus a times r plus a times r to the second, plus a times r to the third, plus a times r to the fourth, etc., 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 all the way to infinity. In a geometric series, both a and r are real numbers, so they're constants, and a can't be 0. The two examples below are examples of geometric series, so let's investigate and see if we can't determine why. The first example A, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. So what is it that makes a geometric series? Well, it's all about the pattern. So let's go back up and look at our definition. Notice in the definition, we have that the first term is a number, so I'll write down when n is 1, then in the geometric series, this first term is what we call the value a. And in the second term, see there's this pattern that develops. So the second term is when you take a and multiply it by some number r. In the third term, what are we doing? We're taking a times r squared. So it's a times r again. In the fourth term, we're taking a times r times r times r. Okay, so there's a pattern that develops. The first term is a, but then sequentially after that, each term gets multiplied by a value r. This kind of should look a little familiar. We finished our discussion not long ago of geometric sequences. And geometric series are very similar to sequences, except we've got this infinite summation going on. All right, so let's look at this pattern. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. In this example, let's start by identifying A. A is the first term in a geometric series, so let's see if this doesn't work. If A is 1, let's see if a pattern doesn't develop. So let's let A be 1. Well, then what would be the second term? So the second term, when n is 2, in the geometric series, that has to be a times r. So if my first term is a, the second term is a times r. So if I've already said that a is 1, what would I multiply by 1 to give me the second term? I would have to multiply by 1/2. Well, that makes sense. That looks good. So, it seems that r is equal to 1/2. I'll write it down right here, but we're going to check it now, okay? If r is 1/2, that means that each term in the series is changed by a multiple of 1/2 each time. So, if I'm going from my second term to my third term, and I'm in a geometric series, that means I need to be multiplying by 1/2. And if I take 1/2 times 1/2, that does give me 1/4. Let me check again. In a geometric series, this ratio r is what I'm getting multiplied by each time. 1/4 times 1/2, sure enough, that gives me 1/8. Let me try one more time. 1/8 times 1/2, that gives me 1/16. Yes, I think this is the pattern. Let's check one more try. Let me just write it out quickly here. Let's see. So if I have that the third term, I'm going to check my notation now, is a times r squared. A is 1. R I said was 1/2. And 1/2 squared is 1/4, and that does match my pattern, just as I thought it would by looking at the ratios. This is a geometric series, clearly. So let's write its infinite summation. So this we could write as the infinite summation n equals 1 to infinity of A times r to the n minus 1, but let's put my values in. So this is the infinite summation, n equal 1 to infinity, of 1 times 1/2 to the n minus 1. Beautiful. It's all about the pattern. That's what we're trying to recognize here. What's the value of A, what's the value of R, and does this satisfy that pattern to make it a geometric series? Let's look at the second example. B, 3/4 plus 3/16 plus 3 over 64 plus 3 over 256. Can you identify the A value and the R value? So again, a geometric series is an A value that stays constant throughout, and then an R value that's a ratio that starts multiplying from the first to the second to the third to the fourth, etc. So in this example, do you see in B that the first term is 3/4, and so that means our A value would just be 3/4. This is the first term, and so I'm going to write down that this A is 3/4. A true geometric series then has this ratio, this number that I'm multiplying through each time. So what would I need to multiply by 3/4 to get 3/16? Well, I would need to multiply by 1/4, right? Because 1/4 times 3/4 gives me 3/16. So that is the ratio that I need to multiply by, and let's make sure that ratio stays constant. So if it's a geometric series, then each term thereafter will come from the previous one by multiplying by 1/4. So 3 over 64, that is 3/16 times 1/4. The next guy, 3 over 256, that is 3 over 64 times 1/4. Absolutely. So R in this example is 1/4. So R is the value that I'm multiplying to get my sequential term, my term after. And so if I want to express this as a summation, I would write n equals 1 to infinity of A, so I'll put my A value in there, times R to the n minus 1. This would be the sigma notation for this geometric series. But more importantly, and you'll see very soon in the next video as we move forward, that even more importantly than writing it in sigma notation is being able to identify A and R. And that's because A and R have a very special place when it comes to the convergence and divergence of a geometric series. So that's what we're going to talk about next.